Hello, in this video I'm going to solve the following problem for you. Let us read the problem together first. Evaluate the following integral. Integral of x cubed dx over x cubed minus a cubed. That would be a good idea if you pause the video at this point and try to solve the problem yourself first. If you do your calculations correctly, this is the answer that you are going to get. X plus a over 3 ln of absolute value of x minus a over 6 times ln of x squared plus a squared minus a over square root of 3 multiplied by tan inverse of 2x plus a over square root of 3a plus a constant c. Okay, let us now solve the problem here. So you see that your integrand is x cubed over x cubed minus a cubed. The first thing that I want to realize here is that a is not 0, because if a is 0, then I have x cubed over x cubed, which is 1, and integral of 1 is just simply x. Yes? So I'm assuming that a is not equal to 0. If a is not equal to 0, then I have a rational expression. A rational expression is a fraction whose numerator and denominator are polynomials. And here the degree of the numerator is 3, the degree of the denominator is also 3. The method that I am going to use to solve this problem is the method of partial fractions. And if you have studied that lesson, so you know that in order to solve the integral using that method, I need a rational expression whose numerator has a degree less than the degree of the denominator. Okay, which is not in this case, which is not the case here. So what I will do, I will try to reduce the degree of the numerator. So I would write this fraction as x to the third minus a to the third, and then plus a to the third, and then divided by x to the third minus a to the third. Okay, so this is exactly as x cubed. And now I write it as x cubed minus a cubed divided by x cubed minus a cubed, and then plus a cubed divided by x cubed minus a cubed. And then this is just simply 1, and then plus, let me write a cubed here, multiplied by 1 over x cubed a cubed. So this means that this integral, which is integral of this function, can be written as the integral of this function plus a cubed multiplied of integral of that function. So if I call my integral I, so I can be viewed as integral of the first function is simply x. Integral of the second function, a cubed is a constant, so it becomes a cubed, and integral of the function 1 over x cubed minus a cubed dx. So in order to answer I, the only problem in my way is to calculate this integral. And if you don't mind, let me just call this integral, for example, j, and then I ask myself, how should I calculate j? But now what is happening here? Again, the type of this integral is as before, because still I have a rational function there. But now if I ask you what the degree of the numerator is, the degree is 0 and the degree of the denominator is 3. So it means that the degree of the numerator is less than the degree of the denominator. So I can apply immediately the method of partial fractions. So what is that method? For method of partial fractions, the first thing that I will do, I will factorize my denominator as much as I can. As much as I can, I mean on the domain of real numbers. And there is a theorem that guarantees that any polynomial of any degree can be factorized into a product of first degree polynomials and or second degree polynomials, of course, with some powers if necessary. So for example, here, if I ask you what is the factorization of x cubed minus a cubed, of course this is famous, this becomes x minus a, x squared plus xa plus a squared. Okay, but in this case, it is important to make sure that this second degree polynomial cannot be factorized more. How can I be sure? For example, I can calculate the discriminant of this second degree function. So it becomes the coefficient of x squared a squared minus 4 times the first coefficient multiplied by the last coefficient. So this becomes this, and this becomes minus 3a squared. But because I am assuming that a is not equal to 0, this is guaranteed to be negative. So when the discriminant of this second degree polynomial is negative, it tells me that this function does not have any zeros. And if it doesn't have any zeros, if this function doesn't have any zeros, it cannot be factorized more. So it is really the complete factorization if I want to work in real numbers, which I have to according to the method of partial fractions. Okay, so what I do, I would write this denominator, 1 over, I would write my fraction as this 1 over x minus a, x squared plus ax plus a squared, and then I decompose it to partial fractions. But how? The denominator of the first one is the first factor, which is a first degree polynomial, so the numerator, I keep it a constant a. And for the second one, I have to write x squared plus ax plus a squared, but this is a really second degree polynomial which cannot be reduced anymore. So in the numerator, I have to write the most generic first degree polynomial. So the degree there should be a first degree polynomial. But the most general one is bx plus c. And then I have to fine tune these a, b, and c so that the left hand side matches with the right hand side for all choices of x. And then you know how to do that. For example, you don't need to look here. I want to get rid of all fractions, so I will take this equality and multiply both sides by the denominator of the left-hand side. If I do that, then on the left-hand side, I will have only one available. And then the right-hand side, when I multiply this fraction by this denominator, this factor cancels that factor, but this is left, which is supposed to be multiplied in the numerator. This becomes a times x squared plus ax plus a squared. And then plus, when I multiply this fraction by the same factor, this time this will cancel that one. X minus a is left, which is supposed to be multiplied here. So it becomes bx plus c multiplied by x minus a. Now I have to open up these and write them in a standard form, which becomes, so let me multiply this, ax squared plus capital A little ax plus capital A little a squared, and then I multiply here, so it becomes bx squared minus bax plus cx minus ca. Okay, so that is a polynomial of degree 2, but it is not a standard yet. I have to write x squared in one location. So this motivates me to factor x squared between these two terms out, and I will be left with a plus b. And then I have 3 terms involving x. So I factor x out. From the last one, positive c is left. From this one, capital A times little a is left, and from this one, minus ba is left. And then I have 2 constants without any x involvement at all. So this becomes plus a little a squared minus c little a. So this is my second degree polynomial. The left-hand side is just 1. I want to fine-tune these constants so that this matches with that one. This can happen if and only if the corresponding coefficients match. So a plus b, which is the coefficient of x squared on the right, should match with the x squared coefficient here, but there is no x squared here. The coefficient is 0. The same is true for this middle coefficient, because I do not have any x term on the left, so this coefficient has to be 0, but the constant term should be equal to 1. So a squared minus ca is equal to 1. Then I have to solve this system. This system includes 3 equations and 3 unknowns, capital A, capital B, and capital C. So don't get confused. This a is just a parameter in the problem. So that's something known. I need to solve a, b, and c in terms of little a. Okay, for example, here I can try to eliminate b, so b becomes minus a, and in this equation instead of b I put minus a, but this is a minus sign, so it becomes plus capital A little a. There is a plus capital A little a here, so it becomes plus 2 capital A little a is equal to 0. So this means that C is minus 2a. Okay? And then I come here, I write it a squared. Instead of capital C, I put this expression, so minus minus becomes plus 2 capital A, but little a times little a becomes a squared, and it is equal to 1. But then this means 3a squared is 1. I am looking for capital A, so capital A is 1 over 3a squared. Okay? And of course I put it here, b is negative of capital A, so it becomes minus 1 over 3a squared. And then c is minus 2 little a times this. So if I multiply by minus 2a, 1a and 1a will be cancelled, so it becomes minus 2 over 3a. So these are my constants. So what does it mean? It means this expression that I am interested to integrate is equal to this plus that for those choices of capital A, capital B, capital C. So if you don't mind, let me write this here. So 1 over x to the third minus a to the third is equal to, instead of capital A, I put that expression. Instead of writing it in the numerator, I write it beside it. So it becomes 1 over 3a squared, and then I have 1 over x minus a. For the next one, I have capital B. So let me write this plus minus 1 over 3a squared x, and then plus c. c is minus 2 over 3a, and then I have x squared plus ax plus a squared. Okay, but let me write it a little bit better or more organized. So for example here, I will factor minus 1 over 3a squared out. Okay, it does not affect the denominator, so the denominator is as it is. But this I pulled out, x is left. This I pulled this factor out. So what is left for me is plus 2a. Yes? Because if you multiply this back here, you will get the first term. And if you multiply back here, one of these a's and these I cancel and I get this. Okay, so now the integral j, which is that integral, is the integral of this part plus that part. So I would write 1 over 3a squared integral of dx over x minus a minus 1 over 3a squared, and then I have integral x plus 2a over x squared plus ax plus a squared. And then I have dx. Okay, but now in order to calculate j, I have two integrals to calculate. This integral, if you don't mind, let me call it k, but this is a very standard one. Both of them are standard ones, but let us just deal them separately and call this L. Okay, so what is k then? K is simply ln of absolute value of x minus a. That's a very standard integral. Of course, if you want to do it step by step, you take x minus a to be a new variable, so you use the method of substitution, but that's extremely easy. But for L, if you remember, you have to do something that the derivative of the numerator appears in the numerator. So the derivative of the denominator is just simply 2x plus a. So if I want to have it here, so L will be equal to, what I do, I want to have 2x plus a in the numerator, but I have x. So I would write 1/2 integral, and then I multiply everything by 2, so this becomes 2x plus 4a divided by x squared plus ax plus a squared dx. Yes? So you see, if I multiply 2 back, I will get exactly this. But then instead of 4a, I just need a. So instead of 4a, I write separately a plus 3a. Okay? So let me write every detail. So this becomes 2x plus a, and then plus 3a, and then divided by x squared plus ax plus a squared dx. And then I separate this integral to two integrals, integral of 2x plus a over x squared plus a squared dx. And then I have 3a, which is a constant. I pull it out, 3a over 2. Then integral of 1 over, so let me write just simply dx over x squared plus ax plus a squared. Okay, so, but then, for example, it is clear that if I take this t in my head, because this one is just a derivative of that one, so this is simply dt. So I know what to do. This is just the standard ln function. So this becomes 1 over 2 ln of absolute value of t, but t is absolute value of x squared plus ax plus a squared. Okay, but what about the second one? The second one should be changed a little bit. So here, if I continue, let me go one step forward, I will write it here up there. So this one is the answer to the first part, plus 3 over a over 2, then integral. That is also a famous method. So you have to write this as x plus a over 2 to the power of 2 minus a squared over 4. And then, of course, I have a squared at the end. Yes, and then I have 1, then I have dx. But you can combine these two as 3a squared over 4. Yes, so let me clean this and write plus 3a squared over 4. Okay, so if you raise it to power 2 and add this to it, it becomes exactly that expression. But what is the benefit of doing that? The benefit is that if you take this one to be capital T, then the derivative of that becomes, so this part becomes dt, and then this is the standard arctangent function. So what happens, it becomes equal to 1/2 ln of, and by the way, I don't need the absolute value sign here. Why? Because x squared plus ax plus a squared, the discriminant of this expression was negative, so it means there are no roots. But this coefficient is positive, so if you draw that, when there is no root, it means the parabola will not intersect the x-axis. And because this one is positive, it means my parabola has a minimum. So if my parabola is supposed to have a minimum and is not supposed to cut the x-axis, it should be somewhere above the x-axis all the time. So it means that this is always positive. When it is always positive, I really don't need to put the absolute value sign. Okay, and this becomes plus 3a over 2. And then this can also be viewed as a square root of 3 over 2 to the power of 2. So it becomes 1 over this constant, and then tangent inverse of this divided by that. Yes? And let me simplify this a little bit. So this becomes 1/2 ln of x squared plus ax plus a squared. And then this 2 and that 2 are cancelled. This a and that a are cancelled. 3 over square root of 3, it becomes just simply square root of 3. Yes? And here I multiply everything by 2. The numerator becomes 2x plus a. The denominator becomes a square root of 3. Okay. So if I come back, be careful, this is just your L. the L is that expression, okay. Yes, so that is my L, and then I have to multiply my L by this constant, multiply my K by this constant, it gives me J, and then I put my J back into the original formula up there, here, and then I will find my X. So let us just do everything now. So let me start from this beginning. I is equal to X plus A cubed times J. So I would write A cubed. This is my J. J is 1 over 3A squared times K. K is ln of absolute value of X minus A minus 1 over 3A squared times L. But what L is the expression that you see here. So if I multiply that here, so let me just multiply it in one go, yes? So I will multiply this by L. So it becomes minus 1 over 6A squared ln of X squared plus AX plus A squared. And then that expression multiplied here. So it becomes minus square root of 3 over 3 becomes the square root of 3 in the denominator, and then I will have A squared here as well, and then I have tangent inverse of 2x plus A over A square root of 3. The final thing is to multiply that A cubed in. Of course, here is a good time to put the constant C at the end. So finally, X plus, if I multiply this in, so it becomes A divided by 3 ln of absolute value of X minus A. I multiply this there, it becomes minus A over 6 ln of X squared plus AX plus A squared. And then finally I multiply this there, it becomes minus A over square root of 3 tan inverse of 2x plus A over A square root of 3 plus a constant C. Okay, and that is the answer that we are supposed to get for this problem. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.